One second. Is it visible to you? Yes, these all our topics are over. Superconductivity, types of superconductors, type 1 and type 2. Then BCS theory, high temperature superconductors, perovskite structures and defects in perovskite structures, high temperature superconductors in cuprates, and phase diagram. Up to here, it is completed. Right. Let us see the next class. The preparation of 1, 2, 3 materials. How we are going to prepare 1, 2, 3 materials, right? The preparation of 1, 2, 3 materials means one metal with one and another one with two compositions, another one with three. 1, 2, 3 materials. These materials are combined with oxygens. Just 1 second. 1, 2, 3 materials. That is YBA2CO3O7, which is a high temperature superconductor. So, which was observed superconductivity at around 90 Kelvin. In some books, 95 Kelvin also will be mentioned, 96 also. Right. How we are going to prepare these 1, 2, 3 materials? 1 yttrium, 2 bariums, 3 coppers. That all are combined with oxygens. That all are combined with oxygens. That is called YBA2CO3O7. Phase diagram we have discussed. Then, so the barium carbonate is mixed with yttrium carbonate, that is mixed with copper carbonate. Then some amount of oxygens will be left over. We can get YBA2CO3O7 minus X by loss of 13 carbon dioxide molecules. Right. In this regard, so what we are going to take, let's see this diagram. Point 454 grams of yttrium oxide, then 1.587 grams of barium carbonate, then 0.9 grams of copper oxide. This all we have to mix with each other, right? Yttrium oxide, barium carbonate, and copper oxide. Therefore, we can get these precursor products mixed together and in mixed with around 3 hours to get a composition of YBaCO. Means yttrium oxide, barium carbonate, and copper oxide. This all the three will be mixed together. We can get a some composition containing powder. Then the grounded sample, that sample should be grounded and taken in a crucible and subjected for calcination. What is meant by calcination means provide high temperature. Provide high temperature. For high temperature, what will happen? Except metals and oxygens, remaining all the elements becomes vaporized into gases. For example, hydrogen will be there, so converted to water and becomes vaporized. Chlorates will be there, that also becomes vaporized. Carbon will be there, that becomes converted to carbon dioxide. Like that, all will be getting vaporized, that is at 900 degrees centigrade. So 12 hours that we can repeat by 5 times, followed by proper grinding. After that, the mixture was taken out and the desired temperature will be reached. So from where, so that calcination means muffle furnace we have to utilize for doing calcination, right? So that calcinated powder will be transferred into, right, muffle furnace, that is around at 930 degrees centigrade. How many 12 hours will be annealed at 500 degrees centigrade for 8 hours in oxygen atmosphere. Finally, we can get YBA2CO3O7-6. This is the procedure to prepare 1, 2, 3 materials. The 1, 2, 3 materials are called, right, superconducting materials, particularly YBA2CO3O7-X. YBA2CO3O7-X. Then this is the simple preparation method and followed by calcination and muffle furnace. So that is the prepared material will be characterized by, right? So there is some characterization will be there. So this prepared material will be characterized by X-ray technique, X-ray diffraction spectroscopy, right? X-ray analysis. This X-ray analysis give the information of the crystal structure of the material. Therefore, from that we can get that is the crystal structure is orthorhombic lattice. And how many kind of elements are there? We told that yttrium, barium, copper, oxygen. 4 kind of elements are there. What about the percentage of those elements that can be identified by method, that is EDTA experiment? Elemental analysis was done by EDTA technique. And what is the resistivity and temperature measurement that will be getting with the help of temperature transition temperature? So the stoichiometric of all these oxygens and other elements, stoichiometry of oxygen and other elements also will be considered with the help of all those information, EDT analysis and XRD analysis and remaining some other suitable methods. Right. So this is the preparation of 1, 2, 3 materials and characterized by various techniques that can produce this, right, prepared material, right. So one more topic is there, that is crystal structure of YBA2CO3O7-X. The crystal structure of YBA2CU3O7-X. What about the crystal structure? Already we discussed that perovskite structures, right? So 3 perovskite structures we have to consider and we have to assemble, means we have to connect all those 3 and we have to remove some amount of oxygens that can give a crystal structure of YBA2CO3O7-X. Okay, right. Let us see the crystal structure. Right. Just here we have to observe. So here each one means this is the one of the crystal structure. The above one is the one of the crystal structure, and the middle one also one of the crystal structure. This is the middle one. There are three perovskite structures will be there. What is the composition of perovskite structure? Already we discussed in the previous class. That is AbO3 is the perovskite structure formula. AbO3. AbO3 is the perovskite structure formula. This AbO3 will be connected. Three AbO3 units will be connected together. You can get this kind of the arrangement. So by connecting of all the three, you can get this structure. The simple connectivity, this is the first one, right? So all will be consisting what yttrium atoms at the center, then copper atoms at the corners, and green will be oxygen at the center of the edges. Right. With the help of this one of the formula, now after connecting the above yttrium, two yttriums will be there. Three yttriums are there. Middle one as it is, we have to write above yttrium and below yttrium. The above yttrium, below yttrium, that can be replaced by barium. The middle one as it is, we have to keep there. Then above one and below one. Just see here. So we have to observe the difference. Here in place of yttrium, barium will be occupied. In place of yttrium, barium will be occupied. In the previous diagram, here same color of the yttrium will be present. Means two yttrium molecules will be replaced with two barium atoms. Two yttriums will be replaced with two bariums. Right. Now, the copper plus 3 is converted to copper plus 2 by removal of oxide ions. Some of the oxide ions we have to remove. Whatever the copper will be present at corner, that will be converted to plus 3 to plus 2. Plus 3 to plus 2, right? Plus 3 to plus 2. During that conversion, number of oxygens will be removed. Therefore, those oxygens will be matches to 7 minus X formula. This is the finally we can get YBA to Cu3O7 minus X crystal structure. Just you people have to remember and have to draw only this diagram in the examination. Only one diagram is enough. Okay. Since how it is getting, so that is for explanation point of view, we have provided three diagrams. Okay. Right. One is, see, here middle will be yttrium. The middle will be yttrium. Here bariums, right? Here copper, and this green will be oxygens. Just observe that here in this phase, here oxygen should be vacant, here oxygen should be vacant, and downside also oxygen should be vacant, here oxygen should be vacant. Means there is a vacancy of oxygens. Here oxygen will be vacant, here oxygen, here oxygen, here oxygen. Means all the 8 oxygens should be reduced from YBA to Cu3O7. Therefore, that will be equals to YBA to Cu3O7 minus X. Means whenever the copper will be reduced, the top, bottom, and side of the middle crystal structures whose oxygens will be removed. This is about crystal structure of YBA to Cu3O7 minus X. So here will be, if you go through the matter, the same thing will be there. First one, we have to connect three perovskite structures of Y2O3, YCuO3, YCU2O3, right? Those YCU2O3, sorry, YCuO3. By connecting of all these three, we can get one crystal structure. From that, two yttriums will be removed with bariums, and after that, copper will be reduced. The number of oxygens will be reduced. Therefore, hence, finally, we can get a crystal structure with less number of oxygen atoms containing one yttrium, two bariums, and three copper. Therefore, that is the final crystal structure. Okay. Right. There is some occurrence will be there, occurrence of superconductivity. First one will be conventional methods. Conventional methods are conventional superconductors. What are meant by conventional? The superconductivity occurs in a number of elements and their compounds. In addition to that, so some large class of alloys also superconducting. What is meant by alloy? Alloy means the mixing of two metals. The mixing of two metals. When two metals are mixed with each other, we can get alloy whose properties will be increases compared with individual. Whatever is the metal, individual metal will be there. What it has some properties, those properties will be enhanced with the help of mixing of one metal with other metal. For example, if you consider iron, iron will undergo oxidation. That is a process known as corrosion. We have to control or stop the corrosion process. What we have to do? One of the metal that should be kept on the iron or that should be doped with iron. Like zinc, like substances will be covered on the iron. Zinc undergo oxidation at the time, iron will be undergo reduction. When iron will be undergo reduction means the oxidation cannot be takes place. Hence, corrosion process should be stopped. That is the process. Right. Then, among all, niobium will be shows highest, that is 9.4 K at atmospheric pressure. In addition to that, the niobium allied smaller and smaller atoms to first class A15 compounds. Right? Instead of that, Mb3Si. Then molybdenum will be introduced, that is Gravel compounds. These are the just examples only, conventional superconductors, available superconductors. Okay. Next one, organic superconductors. What is meant by organic superconductors? Means most organic and organometallics are insulators. Even though some of them exhibits high electrical conductivity. Most of the organometallics or organics will be insulators, but some of the compounds may possess high electrical conductivity. Right. So those we will see what are those and how we are getting superconductivity behavior in that particular materials. Okay. So just remember that this is tetrathiafulvalene, right? Tetrathiafulvalene, TTF. This is combined with tetracyanoquinodimethyl, TNC2. So when these two are combined together or react together in a solvent at room temperature, we can get a charge transfer complex. You can get a charge transfer complex, just organic point of view only. So this charge transfer complex will be, this is the complex we can get. Okay. Right. With the help of this complex, the material resistance will be reduced and its conductivity will be infinity. That material can shows infinite conductivity at particular temperature. So such that that is known as superconductivity material in organic point of view. Here the X is a inorganic anion. In this sulfur and X will be there. This inorganic anion may be PF6, PaF6 and ReO6. So anyone we have to utilize in place of X. Right. Then next you know that about fullerenes. This is the one of the allotropic of carbon. Fullerene is the carbon allotropic form, one of the allotropic form of carbon. So the well-known fullerene is C60, that is called Buckminster fullerene, C60. Right. It has no longer manipulated hydrocarbons. Pure carbon molecules will be present. In addition, these molecules are no longer flat but bulky, which gives rise to three-dimensional structures. This is also known as buckyball, which is consisting 20 hexagons and 12 pentagons, 20 hexagons and 12 pentagons, and whose critical temperature will be around 40 Kelvin, right? So this is fullerenes are grown when invested in closed capsules. The high temperature fullerenes will be observed at CS3, C60, and which is shows superconductivity behavior at 40 Kelvin. Okay. Right. So just you have to observe this. Carbon will be C60, that is combined with the potassium, can shows at 18 Kelvin superconductivity behavior. In addition to that potassium, if rubidium will be added, that will increase the temperature, that is 21.5. At 21.5 Kelvin, it can show superconductivity behavior. And K2CA6 means cesium will be introduced into that closed case structure, right? So it will shows superconductivity at 24 Kelvin, and some other materials which may included in C60 that can shows the temperature will be increases. So finally, rubidium and thallium that are combined with C60 that can shows superconductivity behavior at 45 Kelvin. Right. So this is about entire solid state topic. Right. The solid state topic, in addition to this, some other topic will be there, nanomaterials. Nanomaterials. Right. Means in this fourth black, 2 units will be solid state and other 2 units will be nanomaterials. Right. So now we are going to discuss about nanomaterial. What are meant by nanomaterials? First, you have to know a brief idea about nano. Right. Nano means what is the size of nano size? Means the particles dimensions will be reduced into nano range. What is meant by nano? 1 nanometer is equals to 1 nanometer equals to 10 to the power of minus 7 centimeters and 10 to the power of minus 9 meters. 1 nanometer is equals to 10 to the power of minus 7 centimeters, 10 to the power of minus 9 meters. 10 to the power of minus 9 means 1 by 10 power 9 meters means within a meter 10 power 9 times. That is the size is considered as what nano size. Any three-dimensional system or particles if you may consider that three dimensions will be all the three dimensions are reduced into nano range. Generally, the particles will be present at 1 to 100 nanometers that are considered as nanomaterials or nanoparticles. Nanoparticles are what? 1 to 100 nanometers. Right. Just see this. Right. Just introduction about the nanomaterials. The length range will be usually 1 nanometers to 100 nanometers that are called nanoscale or nano range. Right. The nanotechnology is used to study the structures between 1 nanometers to 100 nanometers in size. Size of the structures, right? Nanostructures that will be under 1 nanometers to 100 nanometer size. Nanoparticles means very small particles. Right? Nowadays, uh, there is a huge research is going on this nanomaterials, right? Because whatever is the big size will be there, particularly in electronic devices, that should be reduced to nano range, right? Then here, so the most important thing we have to understand that is dimensionality, reduced dimensionality of in solids, right? So reduced dimensionality means the cubical system is contains how many dimensions? Three dimensions. X dimension, Y dimension, and Z dimension. Right. If all the three dimensions are present in nano range, all the three dimensions are present in nano range. Right. So that is called what? Nanomaterials. That will be three-dimensional nanomaterials. Right. All the three dimensions will be come under nano range. Right. We'll see. Dimension of the material is reduced from macroscopic size to very small size. Very small size is nothing but nano size. When the size drops below 100 nanometers, there is a drastic changes or occurs in these properties. If one of the dimension will be reduced to nano range, there is a huge changes in their properties were observed. If one dimension is reduced to nano range, which will give quantum wells. Only one dimension will be present in nano range. That are example are what quantum wells. If two dimensions are reduced and one will be remains, that resulting known as quantum wires. If all the three dimensions, all the x, y, z dimensions, right? All x, y, z dimensions, these all x, y, z dimensions will be reduced. all the xyz dimensions will be reduced into the nano range. So therefore, that are known as what? Quantum dots. Just to keep it in mind, three things. One is quantum well, quantum wire, and quantum dots. What are the quantum wells means? Out of all the three dimensions, only one dimension is present in nanos range, means below 100 nanometers. The remaining two will be in large range, other than the nano range. Quantum wires means two dimensions are in nano range. Two dimensions. The one will be above the nano range. Quantum dots means all the three dimensions are present in nano range. Right. These are the substances are known as zero dimensional, one dimensional, and two dimensional. Right. So just we have to observe these diagrams. So from that clearly we know the first one will be bulk. This is the cubical structure. In this, one of the dimension will be reduced means one will be completely reduced into nano range means we can get quantum wells. Quantum wells are nothing but sheet type. Other dimension also will be reduced into nano range means we can get quantum wires. Means wire type. If if all the three dimensions are reduced means we can get quantum dots. These are the quantum dots. Okay, right. If you may consider the bulk in circular path, like circular path, this is the bulk, right? If one dimension will be reduced means we can get a cylindrical type, that is quantum well. So two dimensions will be reduced means like cylindrical also, that is quantum wires. Only simple dot we will get, that is quantum dot. This is the reduced dimensionality in solids. So therefore, with the help of reduced dimensionality, what we are getting means zero dimensionality materials, one dimensionality, and two dimensional and three dimensional. This is the classification may explains about dimensionality of solids. Right. First one is zero dimensions. First we'll go with example and then we'll go with definition and all those things. Right. Fullerene's quantum dots and nano diamonds, which all are called zero dimensional. Zero dimensional quantum dots means now only we discussed that all the three dimensions are present in what? Nano range. All the three dimensions are present in nano range, that is called quantum dots. Such kind of materials are zero dimensionality materials. Okay. Right. Yes. Am I audible? Yes, small issues are there at my side. Am I audible? Okay. Yes. Yeah. Now we are at zero dimensionality, right? Zero dimensionality means fullerenes, quantum dots, all. All the three dimensions are present in nano range. Okay. Then one dimensional means only one dimension will be present in the nano range. Other two will be other than the nano range. Example, carbon nanotubes and carbon nanohorns. And coming to the part of two-dimensional. Two-dimensional means graphene, nanoribbons, and few layered graphenes. These all are two-dimensional. In two-dimensional means one dimension is in nano range, other two will be in other than the nano range. Then coming to the part of three-dimensional materials. All the three dimensions are in out of the nano range. So which is nanoparticles, bundles, and nanowires, nanotubes, and as well as multi-nano layers. Right? So this is about zero dimensionality, one dimensionality, and two dimensionality. Right? So what will happen by reducing one dimensionality of the material? Right? So just we'll see zero dimensional materials. Metals in which all the three dimensions are within the nano range. Therefore, that is called zero dimensionality. What is the nano range? That is the 1 to 100 nanometers. 1 to 100 nanometers. 1 nanometers to 100 nanometers is the nano range. All the dimensions will be reduced into this range. Means nano range. We can get zero dimensional materials. The most examples of zero dimensional materials is nanomaterials or nanoparticles. Nanomaterials, nanoparticles. Right. So these nanoparticles can be various, means possess various properties. So just go through all these properties. Amorphous or crystalline. Amorphous or crystalline. Next. Single crystalline or polycrystalline. It is composed by singular multi-chemical elements. Single chemical element or multi-chemical element. Exhibits various shapes and forms. Exhibit various shapes and forms. Exist individually or incorporated in a matrix type, which may be metallic, ceramic, or polymeric. This is about the nature of the nanoparticles. Means that can possess nanoparticles can possess all this kind of the properties. Okay, right. Coming to the next slide. Simple thing, just you have to understand zero dimension means all the three dimensions are reduced into nano range, right? All the three dimensions are reduced into nano range. That is called zero dimensional nanomaterials. Okay, right. So here all the dimensions XYZ dimensions are at a nanoscale only. So therefore such materials are nanoparticles. Example will be fullerenes. Just now we discussed fullerenes, right? This is also known as soccer ball. Right. One more thing, one more time we have to go through it. So what it has properties, right? Fullerenes are the closed case structure materials by the presence of 5-membered rings and as well as 6-membered rings. Right. It has containing 12 hexagonal and 20 hexagonal and 12 pentagonal phases, pentagons also. We may call as 20 hexagons and 12 pentagons. Hexagons means like benzene like structure, but we don't have double bonds. Pentagons means 5-membered rings. Like 12 5-membered rings and 20 6-membered rings all are connected together in a cage like structure. Therefore, we can get Buckminster fullerene, that is C60 fullerenes. Right? C60 fullerenes. In the C60 fullerenes, arrangement of atoms are in non-planar and slightly pyramidalized, and the result will be sp3 hybridization, binding, and the carbons will be possess sp2 hybridization. Means in fullerenes, carbon will be possess sp2 hybridization. Among all, C60 will be well-known material, which consisting 12 hexagonal and 12 pentagonal and 20 hexagonal structures. So this is exactly similar to the soccer ball. Right now, FIFA is going on soccer matches, right? Football, you all people know. So that will be consisting like this C60 type of the structure. Okay. So this is the like soccer ball. So here 5-membered ring, just observe that. Here this is the 5-membered ring. Sorry. This is the 5-membered ring. Then this is the 6-membered ring. Next is 6-membered, 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 6-membered. One 5-membered ring is connected with all 6-membered rings surrounding. So next one will be again here 5-membered, here 5-membered, here 5-membered, right? Here 5-membered, here 5-membered. Like that, 12 5-membered and 20 6-membered hexagonal and pentagonal rings will be so joined together to form like a FCC structure. FCC structure. What is meant by FCC structure? Face-centered cubical structure. Face-centered cubical structures means all the atoms are present. For example, here this is the cube. Just I am going to write. This is the cubical structure. Right. All the atoms are present at all the corners. Total 8 corners will be there. These all 8 corners will be occupied with atoms. As well as corners, faces also will be occupied. Right. One phase, two phase, three phase, right? Fourth phase, fifth phase, and sixth phase. All the 6 phases and 8 corners will be occupied with elements. That is the structure is known as what? FCC structure. FCC. Okay. Right. So in this, van der Waals diameter will be around 1.1 nanometers, and it is super aromatic. It is said to be not a super aromatic. Right. It is said to be not a super aromatic. Then a pure delocalization of electrons will be takes place. Pure delocalization of electrons will be takes place in this, and somehow properties which will be possessed by the C60 fullerenes. Then one more will be example we discussed that quantum dots. Just remember zero dimensional means quantum dots and fullerenes, right? So these are the examples for zero dimensional, right? So what are the quantum dots? Let us see. Just go through the information only. Right. Particularly in quantum dots, carbon quantum dots will be well known, right? Carbon quantum dots, CQDs, we may call as CQD, carbon quantum dots. Quantum dot is a crystal, few nanometer wide, which is a tiny speck of meter and so small, effectively concentrated into a single point. Right? So this is about quasi-spherical carbon nanomaterials. The diameter range will be 2 to 10 nanometers. All the three will be present in nano range. Therefore, hence it is a zero-dimensional. And each carbon is possess sp2 hybridization in this. The aggregation of in aqueous solution, they may get aggregation, right? This is. There are huge applications of quantum dots, carbon quantum dots will be there, right? Particularly, we will see. Right. The biosensor-based quantum dots could be used for visual monitoring and pH, then glucose and nucleic acids. And also, this will be potentially applicable for dye-sensitized solar cells, organic solar cells, then supercapacitors, LEDs, light emitting diodes. So presently we are using the televisions and mobile phones, all displays will be like laptops, displays will be LEDs only, light emitting diodes. Previously LCDs will be there, right? Light compact device. Right now LEDs we are utilizing. So for making of LEDs, the concept of nanotechnology can be utilized, and particularly purification of water, right? That is a various good applications of photocatalysis will be there. And there are many bio applications will be there due to visible excitation and emission wavelengths. Visible excitation and emission wavelengths. So based on that, there are huge bio applications will be there. Right. Some other applications, these are drug delivery and will be there. So now coming to the part of one dimensional. One dimensional means other two dimensions are present in nano range. One dimension is other than nano range. Just go through the definition. One dimensions are the materials not confined to the nanoscale in one dimension. Means one dimension is not within the nano range. The other two will be within the nano range only. One that is one dimension is outside the nanoscale. Okay. One dimension is outside the nanoscale. The other two will be present in within the dimensions. This leads needle-like shaped materials, nanomaterials, like nanotubes, nanorods, nanowires. Right. These are the properties which are applicable for one-dimensional. Amorphous or crystalline, single crystalline or polycrystalline, chemically pure or impure. Then standalone materials are embedded in within another medium. Then metallic, ceramic, or polymeric. Metallic, ceramic, or polymeric. Right. So these are the properties which are applicable by one dimensional. Right. So this one dimensional example will be carbon nanotubes. If the two dimensions x and y are present in nanoscale, the other dimension L will be out of the nano range. This is the L dimension will be out of the nano range. Therefore, we can get like a rod or wire type of the structures. Okay. Therefore, here a small discussion about nanotubes, right? Particularly carbon nanotubes. These are the allotropes of the carbon with a cylindrical structure with the diameter is less than 100 nanometers and can be thin as 1 or 2 nanometers, right? Which will be very thin materials and possess various properties. So just with the help of diagram, we have to understand. Right. Single-valved nanotubes will be there and multi-valved nanotubes will be there. This is nothing but what? Single-valved nanotubes, multi-valved nanotubes. Single-valve and multi-valved nanotubes are there. So this is the graphene material. This will be rolled up means we can get only single valve. Graphene is a one of the material that can be rolled up. We can get a single valved nanotubes. If many graphenes will be rolled one upon another, we can get a multi-valved nanotubes. There are huge importance of single-valved and multi-valved nanotubes in nanotechnology. These are particularly examples for what one-dimensional nanomaterials. Okay, just you can go through the synopsis only, so just how it should be. Right. There are applications of carbon nanotubes will be there. Right. That are carbon nanotubes, one-dimensional that is used in batteries, used as the capacitors, and used as the catalysis, used as the sensors, used as the membranes, used as actuators, then used as transistors, used as killers. These carbon nanotubes having more importance whenever two dimensions will be present in nano range, other one will be out of the nano range. Such will be example of one-dimensional nanomaterials. Right. So this one-dimensionality in this one-dimensionality, so we can get such kind of things. So then we have some preparation methods of nanomaterials, right? So particularly top-down and bottom-up method, then followed by salt gel method, then followed by chemical vapor deposition method, right? After that, somehow characterizations will be there. So those preparation methods and characterizations of nanomaterials that will be discussed in the next class. Now, just you have to see what is meant by dimensionality. What is meant by dimensionality of the solid materials? Zero dimensions, one dimensions, two dimensions, and three dimensions. Three dimensions are nothing but all the three will be out of the nano range. That is bulk molecules only we have to consider. Okay. Right. Yes. Any doubts will be there? Just you can post in the chat box. No? Even in solid state or even in nanomaterials of today's class. If any doubts will be there, just you have to share a message in the chat box. We'll discuss that. Yes. In the next class, you can conclude this nanomaterials. So then, photochemistry, thermodynamics have covered in offline classes. So one more quantum chemistry will be there. We can discuss that quantum chemistry. And somehow people are asking notes. So today I will share these notes in the WhatsApp group. You may circulate. Yes. Any doubts from solid state? Yes, ma. Respond. Any doubts are there?
No, sir.
Okay. I can share the notes, no issue.
Okay.
These two topics.